Hello, and welcome back to our series on multiple linear regression analysis. So, in our last video, we talked about outliers, whether we should remove them or not, and if you wanted to remove them, how it would look like. We also then built our model. So, now that we've built our model, we should start exploring the output a little bit. So, the first thing that we're going to do is we're going to grab our intercept and our coefficients. So, we're going to create basically some new variables stored in there, and then we're gonna loop through it. So grab the intercept and the coefficients, and then so what we're gonna do is do intercept equals regression underscore model, and then we're gonna do intercept, and then actually it's kind of good to show for demonstration purposes. Intercept, sorry, underscore, my bad. And so you can see it's in an array, and so I just want to grab the first element, just like that. Same kind of logic for the coefficients, and so we're just going to say regression model dot coefficients underscore, and then it's the 0, and then it's another 0, and just like that. Perfect. I have some stuff where we already printed out, just for time's sake, so I'm going to just do that, and then I'll kind of explain what I'm doing. I rather focus more on the concepts and printing. Okay, so this one is just going to print out the intercept little line thing. This is probably the part that, if anyone gets lost, it would be right here. All I'm doing is I'm zipping up each column name with the corresponding coefficient, and then all I'm doing is just printing it out. So really, I could kind of just do that if I wanted to and just put it right over here as a variable. Again, it's up to you how you want to do it. I'll just put it like that. We'll just do coefficient just like that. And then I'm just going to be looping through it. Well, just so we do that. Perfect. And so when we do this, it prints out the intercept. My intercept is 2.08. And then we have population growth, and then we have broad money growth. So these are just kind of all the ones that we're looking at. And then I think right down here, I kind of give you how you would interpret it. So if all the variables were 0, GDP growth would be 2.08%. And then, for example, gross capital formation growth, if I provide 1 unit of that, you would expect to see a 0.14% increase in GDP growth. So that's really all it's telling us at this point. So this is just printing it out and then interpreting it. So again, if all the variables were 0, this is what it would look like. And then if I add 1 unit here, then you would expect to see 1% population growth translates into 2% GDP growth. And so on and so on. So very interesting. This is actually pretty high for the most part. But from here, if you wanted to, we could also make predictions. We have to make predictions if we want to get some residuals. So what we'll do is we'll get some predictions, get multiple predictions. And so we'll call it y underscore predict. And that equals the regression underscore model dot predict. And then we'll do the X test. So we're going to take the X test set, and then we're going to do some predictions. And then just show the first 5. And so if I go Y predict, and then I'll slice that array and say, just give me the first 5. And there you go. You got your first 5 predictions. All right, so now that we've done that, we're going to move into the fun part, probably the more complicated part, which is evaluating our model. So in order to evaluate our model, we're going to be using the stats model API. The reason why is everything there is just wonderfully already pre-built. And so I rather leverage that because I think it will kind of make things easier on your end. However, what this is going to require us to do is actually kind of rebuild our model, but using the stats model API. Everything else should be coming out exactly the same. There might be slight variances here and there, but generally speaking, the model should be the same. And so how we're going to do this is we're going to define our new X variable that equals the stats model. We're going to do the add constant. It does expect a constant. And then so here we're just define our input And then from here, we're going to create an OLS model, ordinary least squares regression. We'll set it equal to a new variable called model SMOLS. We'll pass through our y, and then we'll pass through our x squared. So we can use the original y, but our x does have to have a constant associated with it. And then we can fit the data. And so we'll say our new estimate equals model, and then we'll call the fit function. And then this will pop up. Don't worry about that. Well, actually, I don't know if it will pop up. I just updated a lot of my libraries, so it's very possible that this is just something in their library. Don't worry about it. Everything should work the same. If most people haven't updated, I don't think you're going to see the error. Okay, so now that we've done that, let's go and talk again about our assumptions. Remember that one of the assumptions about our model is that there is no heterodacity. In other words, the error terms stay constant. So we do not see a change in the error terms. Now, I do have a little definition here. So I like to kind of read through it. I think hopefully, that kind of reinforces the idea. Again, a simple definition. It merely means the standard errors of a variable monitored over a specific amount of time are non-constant. So I found this little example online that I thought was interesting. I think it helps kind of drive home the concept. Imagine we modeled household consumption based on income. Something we would probably notice is how the variability of consumption changes depending on how much income you have. In more simple terms, we see that households with more money, with more income spend money on a broader set of items. So they kind of spend more money on all these different types of things compared to lower income households that would only be able to focus on the main staples. This results in the standard error that change over income levels, because you're seeing this variation where at high income levels, you're seeing this wide spending pattern where at a lower income level, you're not, because the person just doesn't have as much money to spend. They're focusing more on the staples. So this is something where over the same group, you can see a variation in the standard error. This would be an example of heterodacity. What we would want is that error to stay constant over both groups. So what's the problem with heterodacity? Well, while it doesn't cause bias in the coefficient estimate, it does cause the coefficient estimates to be less precise. The lower precision increases the likelihood that the coefficient estimates are further from the correct population value. So in other words, we're just saying that it's not that they're biased, it's just that they're not, it's less precise. So it's probably further away from from the actual value than it is. Heterodacity also tends to produce p-values that are smaller than they should be. And so if they're smaller than they should be, that means potentially we could keep something that we should be rejecting. And so that's another problem. We don't want our p-values to be impacted too much, because then that can create a situation where we're keeping something that we shouldn't be. And so there's different ways that we can check for heterodacity. One of the tests that we can do, and I'm probably going to just missay this test. I'm going to call it the pagan test. But basically here, what we're going to be doing is we're going to be doing a null hypothesis. We're basically going to be testing a hypothesis. There is another test called the White's test. This is a more specific version of the pagan test, but their null hypothesis is the same for each. So the null hypothesis is that the variances of the errors are equal. And then the alternative hypothesis is that they are not equal. And so our goal is to fail to reject the null hypothesis. We want to have a high p-value, because if we have a high p-value, it means that we cannot reject our null hypothesis. And the null hypothesis is that the errors are equal. And so in other words, they're constant over time. They're constant. And so now, with any test, it's not going to say 100% for sure there is no heterodacity. We can just say it with a higher level of confidence. That's really the goal behind this. And so I don't know if I have to or not. I think I already imported it up here. I got to double check though. I did. Okay, perfect. Yes. No. We'll see in a second. Okay, so what we're going to do is we're going to call the diagnostics, and then if I do tab hetero white, yeah. We'll just do both to be safe. Yeah, we'll just do both. So we'll do both tests. I mean, technically, there's a lot of debate if the whites test is even one that we should be using, but at this point, let's just assume that's right. All we're going to do is we're going to pass through the residuals of our model, and then we're going to define some stuff. So we're going to take the exogenous variable, and then there's one final one that's retries and then false. Okay, and then this is going to return something back to us. So it's this wonderful little tuple. The parts that we're concerned about are this one and this one. So these are our p-values and our f-value. And so what we'll say is _1 is p-value, and then comma, underscore, comma, and then f p-value. And then that's really the test. I know that's a lot of work, right? And then what we'll do is we'll print the p-value and the f p-value. And then finally, I'm going to do my little thing where I take this one and times it by 100, just like that. So here we are running the white test. And then all I really have to do is I'm going to take this one and I'm just going to change it. See, I don't like when it does that because I try to be, okay, I want the pagan test. And I want this one. Perfect. Now, this one takes everything except this one. We just got to remove that last parameter. And so basically here, the p-values are much greater than 5, so we fail to reject the null hypothesis. Now, I did put a nice little condition here. I think it's nice. I'll just show it to everyone just so you can have access to it if you want. It's just a simple if statement, so I'm just saying, if it's greater than 5, you can fail to reject. So that's all it is. So for the whites test, the p-value was such and such. We fail to reject the null hypothesis, so there is no heterodacity. I mean, we can't say 100% for sure, but we can say with a high level of confidence there is no heterodacity. And then with the pagan test, there is also no heterodacity. So again, this is just kind of reaffirming one of the assumptions of our model, which is there is no heterodacity. So there is basically the error terms are constant over time, which is great. That's what we want. Okay, the next thing, checking for autocorrelation. So what is autocorrelation? Autocorrelation is a characteristic of data in which the correlation between the values of the same variables is based on related objects. It violates the assumption of instance independence, which underlies most of the conventional models. When you have a series of numbers and there is a pattern such that the values in the series can be predicated based on preceding values in the series, so the values before it, the set of numbers is said to exhibit autocorrelation. This is known as serial correlation and serial dependence. It generally exists in those type of data sets in which the data, instead of being randomly selected, are from the same source. With time series data, it's very likely there is autocorrelation. In fact, this is something I didn't cover in the previous video on the simple linear regression model because I kind of didn't want to get into it at that point. But our data set was highly, we had a ton of autocorrelation. There are ways to fix it. I'm not going to explain it in this video because we're going to find that there is none in our data set, but there are ways to fix it. And really, what is the problem with autocorrelation? Basically, it just means that the computed standard errors and consequently the p-values are misleading. Autocorrelation in the residuals of a model is also a sign that the model may be unsound. It basically means that you probably picked the wrong model. And so what we're going to see is there's another test that we can run that will allow us to detect whether there is autocorrelation in our data set. In fact, there's actually a visuals too that we can also leverage if we wanted to. Oh wait, no, that's a different topic. sorry, disregard that one. But yeah, there's different things that we can do to kind of test whether there is autocorrelation in our particular data set. And so that's what we're going to cover next. Okay, so how do we test it? Well, there is a test called the lung box test. It's basically right up here. And with this one, we can pass through our residuals. And what we have to understand here is the null hypothesis is the data are random. And then the alternative is the data are not random. So in this situation, we want to fail to reject our null hypothesis. We want a high p-value so that way we can fail to reject the null hypothesis, which is basically saying there is no autocorrelation. So what are we going to do? All right, well, we're going to call our diagnostics. Wonderful thing that we did right up here. We're going to call our diagnostics, and then from here, we can do autocorrelation, Young box test. Oops, sorry about that. And then we're going to pass through, again, our residuals. And then there's this parameter called lag. And so we can either calculate the lags or we can let the model do it itself. There's kind of debate on which one is that you should be using. There was one that I found online that I thought was interesting. Basically, what we do is we can either say it's going to be the minimum of 10, or we can say it's going to be the minimum of our data set divided by 5. And so we're just going to take the minimum of either one of those. That's kind of like one of the ones that I think they had for non-seasonal data. And so we didn't have seasonal data. And so in that situation, we could use this method for calculating the lag. And so what we'll do is we'll create a new variable called lag, and that will equal the min of 10, or, and then here's the fun part, we're going to calculate the length of our x, hard floor division, and then 5. So this will basically just round it off to whatever it comes out to be. And then so here we're going to calculate the lag, and then we're going to be performing the test. So perform L Young box test, just like that. And then I have some stuff in here too that I'm just going to leverage. Sometimes it's just better to set it up. Okay. This is, again, just for more visualization purposes. This will just print out the number of lags that it's calculated to. Oh, sorry, not there. X. And then this one is performing the test. And then so we'll equal the test results. Just like that. And then here I'm going to grab the p-value and the b-value and all that stuff. So that's fine. And then it's the same kind of method that I was doing up here. So I'm just going to be saying, hey, just print out everything that we have. And then from here, so basically the lowest p-value that was found was 15.96. And then we failed to reject the null hypothesis. So there is no autocorrelation. I think it kind of helps too if I just print out the test results so you guys can see kind of what's going on right here. So it comes back with this array, of all the p-values. And so what we're basically saying is give me the lowest one, because that's the one where, again, the lowest one potentially, because if it's the lowest, then what we can say is, oh, well, if it's below 5, then this is one that we can use to reject our null hypothesis and accept our alternative hypothesis. So this one just comes back with an array, and all we did was we found the minimum within that array. That's all we were doing. So hopefully that makes sense. And then again, we're just splitting it. So this is the p-value array, and then this was the b-value one. We can also, if you want, and this is kind of what is nice too, is we can actually graph it as well too. So we can plot autocorrelation. This is one of those cool ones that I think comes with the stats model library. And so we can do stats model graphics. Where is it? Graphics, and then TSA, and then plot autocorrelation, and then estimated residuals, and then plot.show. Cool. And so disregard the first one, but basically you don't want these values going outside this little blue range because that can be a sign of autocorrelation. So that's basically autocorrelation in a nutshell. And so again, in our data set, there is no autocorrelation. So we can kind of check off that box as well. So we don't have heterodacity, we don't have multicollinearity, and we don't have autocorrelation. So we're meeting most of the assumptions right now of our model, which is awesome. I like to think of it as like a checklist. You're going through your checklist, making sure that everything's working the way you're expecting it to, and then you move on to the next stuff. So with that being said, I am going to cut off the video right here. So if you have any questions about heterodacity or autocorrelation, please put them down in the comments below, and I will try to get back to you. In our next video, we're going to be talking about a few more assumptions of the model, and then I think after that, we can actually get into the part where we're saving it. I think there's another part where I actually go through and I kind of remove the variables, but we'll kind of explain that when that point comes up. So thanks again for watching, guys. We'll see you in the next video.